Imagine the entire universe squeezed into a space smaller than an atom. This tiny, incredibly dense point held all the matter and energy that would eventually form everything we know today. This incredibly dense and hot point is what scientists call the singularity. The singularity is a concept that defies our current understanding of physics, where the laws of nature as we know them cease to apply. It's hard to believe, but this is where our universe began. From this singularity, an unimaginable explosion of energy and matter occurred, setting the stage for the creation of everything. About 13.8 billion years ago, the Big Bang occurred, and everything exploded outward. This wasn't just a simple explosion, it was the rapid expansion of space itself, stretching and growing at an incredible rate. This event wasn't an explosion in space, but rather the expansion of space itself. Imagine a balloon being inflated. As it expands, every point on the surface moves away from every other point. This is similar to how our universe expanded. The Big Bang theory is the prevailing model explaining the universe's origin. It provides a comprehensive framework for understanding how the universe has evolved over billions of years. It's supported by a wealth of evidence, including the redshift of distant galaxies. This redshift indicates that galaxies are moving away from us, suggesting that the universe is still expanding, and the existence of the cosmic microwave background radiation. This faint glow left over from the early universe provides a snapshot of the cosmos when it was just 380,000 years old. This theory helps us understand how the universe evolved from a tiny point to the vast cosmos we observe today. From the formation of the first atoms to the birth of stars and galaxies, the Big Bang set everything in motion, leading to the rich and complex universe we are a part of now. As we continue to explore and study the universe, the Big Bang theory remains a cornerstone of our understanding, guiding us in our quest to unravel the mysteries of the cosmos. The singularity wasn't just small, it was infinitely dense and hot. All the matter and energy that make up the universe today were compressed into this single point. Time, as we know it, didn't exist before the Big Bang. The singularity represents the very beginning of everything. While we can't observe the singularity directly, scientists have developed mathematical models to understand its properties. These models suggest that the singularity was governed by laws of physics that we're only beginning to comprehend. The conditions within the singularity were so extreme that they challenge our current understanding of physics. In the first fraction of a second after the Big Bang, the universe expanded rapidly. As it expanded, it cooled down. Imagine a balloon inflating. As it gets bigger, the air inside becomes less dense and cooler. The same principle applies to the early universe. This expansion and cooling allowed energy to convert into matter. Subatomic particles like quarks and electrons formed from the primordial energy soup. These particles interacted with each other, eventually giving rise to the building blocks of atoms. As the universe continued to cool, protons and neutrons combined to form the first atomic nuclei. The vast majority of these nuclei were hydrogen and helium, the two lightest elements in the periodic table. These elements would later play a crucial role in the formation of stars and galaxies. For hundreds of thousands of years after the Big Bang, the universe was a hot, dense soup of protons, neutrons, electrons, and photons. Light couldn't travel freely through this plasma. It constantly scattered off charged particles. The universe was opaque, like a thick fog. Section 5. The Cosmic Microwave Background, an echo of the Big Bang. Around 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with atomic nuclei, forming neutral atoms. This cooling period was crucial because it allowed the universe to transition from a hot, dense plasma to a more stable state. This event, called recombination, marked a significant change in the universe's history. During recombination, the charged particles that once scattered light were now neutral, allowing photons to travel unimpeded. Light could finally travel freely without being scattered. This newfound transparency of the universe meant that light could journey vast distances, carrying with it the story of the early cosmos. The light released at this time has been traveling through the universe ever since. These ancient photons have traversed billions of light years, providing us with a direct link to the universe's infancy. Today we observe it as the cosmic microwave background radiation, a faint afterglow of the Big Bang. This radiation is a crucial piece of evidence supporting the Big Bang theory, offering insights into the conditions of the early universe. This radiation provides a snapshot of the universe as it was just 380,000 years old. By studying the cosmic microwave background, scientists can learn about the universe's composition, structure, and evolution, helping us understand the fundamental forces that shaped our cosmos. Section 6. The birth of stars. Gravity's role. Over millions of years, gravity began to pull together the vast clouds of hydrogen and helium gas that filled the early universe. These clouds became denser and hotter, eventually reaching temperatures and pressures high enough to ignite nuclear fusion. This marked the birth of the first stars. These early stars were much more massive and short-lived than our Sun. They burned through their nuclear fuel quickly, ending their lives in spectacular supernova explosions. These explosions scattered heavy elements forged in the star's cores into the surrounding space. Section 7. Galaxies form islands in the cosmos. As stars formed and died, gravity continued to shape the universe on a larger scale. Vast collections of stars, gas, and dust were drawn together, forming galaxies. Our own galaxy, the Milky Way, is just one of billions of galaxies in the observable universe. Galaxies come in a variety of shapes and sizes, from spiral galaxies like our own to elliptical galaxies and irregular galaxies. They are constantly evolving, interacting with each other through gravitational forces and mergers. Section 8. Dark matter and dark energy mysteries of the universe. While we've learned a great deal about the universe's origin and evolution, many mysteries remain. One of the biggest puzzles is the existence of dark matter and dark energy. These mysterious substances make up the vast majority of the universe's mass and energy. Dark matter doesn't interact with light, making it invisible to our telescopes. However, its gravitational influence can be observed on visible matter, suggesting its presence. Dark energy, on the other hand, is a hypothetical form of energy that is causing the universe's expansion to accelerate. Section 9. The expanding universe, a never-ending story. Observations of distant galaxies have shown that the universe is not only expanding, but that its expansion is accelerating. This discovery has profound implications for the fate of the universe. Will it expand forever, or will it eventually collapse upon itself? The answer to this question depends on the nature of dark energy. If dark energy continues to dominate the universe's energy budget, the expansion will continue to accelerate, leading to a big freeze scenario where galaxies become increasingly isolated. Section 10. Conclusion: the universe's unanswered questions. The study of the universe's origin and evolution is an ongoing journey of discovery. For centuries, humans have gazed at the stars, wondering about the mysteries that lie beyond our planet. While we've made remarkable progress in understanding the Big Bang and its aftermath, many questions remain unanswered. The more we learn, the more we realize how much we still don't know. What is the nature of dark matter and dark energy? These elusive components make up most of the universe, yet we can only infer their existence through their gravitational effects. Are there other universes beyond our own? The concept of a multiverse suggests that our universe might be just one of many, each with its own laws of physics and unique properties. Scientists are constantly seeking answers to these fundamental questions through observations, experiments, and theoretical models. They use advanced technology and innovative methods to probe the depths of space and time. The universe is a vast and mysterious place, full of wonder and awe. Every discovery opens up new questions and possibilities, fueling our curiosity and drive to explore further. As we continue to explore its depths, we can expect to make even more astonishing discoveries in the years to come. The quest for knowledge is never-ending, and the universe holds countless secrets waiting to be uncovered. Each step forward brings us closer to understanding the grand tapestry of existence, inspiring future generations to look up at the night sky and dream of what lies beyond.